Welcome to the last lecture in renewable energies. I was pondering a little bit what we still could discuss today. There would be so many things, of course, but I have to do a selection. And of course, I also wanted to have it a little bit, well, perhaps not so math heavy than the other lectures that you have heard. And I hope you enjoyed at least some of them. I will start with a little experiment that I did with wind turbines. So let me switch to the presentation. So what you see here is, of course, the title page but now the next one. I did, as I said, a little experiment, and what I did was to use my camera drone in order to inspect a windmill. So what I wanted to know in particular was how turbulent the wind would be behind the blade. And actually, I felt a little bit uneasy to do that, because what I realized, and actually what was clear to me, is that in such a distance, so if you fly, say, 50 meters high, 100 meters high, in such a distance you can't really judge well the distance to the blade. And of course, I didn't want that my drone would be crashed by the blade. Actually, just today, this drone crashed. Because I wanted to take a few nice winter pictures, and it was the same problem. I couldn't judge the distance, and so it crashed, but fortunately we were able to recover it. Okay, so this is actually a small wind park, and you just see one of the 3 windmills in this small wind park. This is actually close to the small farm where I grew up. Yeah, so somewhere in Franconia. So these few houses there, this is where I grew up. Yeah, so actually in this house here. Well, let's run it and just watch this windmill here a little bit. And actually, I stand next to another of these 3 windmills, and we will look at this windmill in particular. So here you slowly see that the tower of that windmill comes into the picture. And yeah, well, let's go to the next part. And here the drone already flies pretty much at the height of the gondola of the machine house. And well, the idea was to sit behind the blade in order to watch, in order to see what kind of, whether actually the turbulences are so strong that the drone perhaps even crashes. Well, nothing has happened, so I just fly higher and higher, and because everything went so smoothly, I decided that I should place the drone just behind the tip of the blade, because we learned that the turbulences there are strongest. So I flew up, and now now it should go down a little bit. No, it doesn't do that. Something happened to my video. Well, sorry for that. Let us see this video in its original shape. Let me see where I have it. Sorry for that. So here we have it again. So you see myself here next to the tower. And now let us go forward for 2 minutes and a little bit more, right? And you see, so this is what we saw, right? And next I'll lower the drone, just that the drone sits behind the tip of the blade. I hope it works. No, it should work. Yeah. So it slowly moves down. Yeah, you see that I'm a little bit cautious and nervous, obviously. Yeah, and then in a few seconds you'll see that at the lower edge of the movie, the blade would appear slowly. Just be patient. Yeah, here it comes. Yeah. And now you have to watch carefully. Yeah? So you see that when the blade arrives, then there is a small jitter in the frame. Yeah? Yeah, so here you see it particularly well. Yeah? And this is when we see the tip vortices. So this is the effect, the obvious effect of the tip vortices. Well, this was just for the fun, of course. Actually, what I plan to do at some point would be to equip the drone with a smoke generator in order to watch the smoke, so the colored smoke perhaps behind the windmill and see how it works. Okay, anyway. We want to do something different today. Namely, we want to look at the concepts of electricity generation with these windmills. They are different concepts, and I have to admit that I'm by no means an expert in this high power electricity generation. It is, of course, its field with a long tradition on its own, but a few basics I would like to discuss. So this then would be chapter 8, say. Yeah? So chapter 8. And I give it a strange headline. Yeah? This and that on wind power. So, and the first one would be concepts of electricity generation. And I would start with giving a brief introduction in some basics that are actually stolen from my lecture in the second semester. Those who attended that lecture might remember it. But first, let me write down the headline. Yeah, so the essential thing is that we have to discuss three-phase electricity, because whenever you speak about high power in electricity, then it's three-phase electricity, Drehstrom in German. So let's start with a few slides from the second semester. So here you see some pioneers of that field. Yeah, Galileo, Ferraris, still known from the old-fashioned electricity counters that many of you, well, your parents perhaps, have installed in your house. They are, of course, now replaced by digital versions. But until very recently, they were ubiquitous. Actually, even in my house, they originally installed such an old-style electricity counter as invented by Ferraris. Nikola Tesla, of course, everybody knows, and Mikhail Dobrovolsky he's probably much less known, but actually a very important figure. He exiled Russia because he was liberal and the Tsar was not, maybe similar to today. And he became, I think he was with REG, with the company REG, and was of pivotal importance in developing three-phase electricity. So he led the project of the first three-phase electricity line from Laufen, which is a small place where they produced hydropower, right? And then this electricity was transported over more than 100 kilometers to Frankfurt, and they illuminated here some fair, and this was spectacular. It was quite efficient, this electricity transportation. Well, if we speak about motors or generators, then we have to distinguish two types, namely the asynchronous generator or motor and the synchronous machine. And so the asynchronous machine is very simple in principle. So it consists of this stator. So it produces a rotating magnetic field, and inside there is this cage. So in German it's called Kurzschlussläufer. In English, I think it's called Squirrel Cage, Eichhörnchen, so Tretmühle or something like that. It's really just what is depicted here. There's no connection to the outside. What happens is when the magnetic field changes, that currents are induced here, and these currents in turn produce, of course, also magnetic fields, and this puts this thing here in rotation if it's a motor. If you have a generator, then of course you would rotate this thing, and then electricity would be induced in the stator coils. So why is it called asynchronous? It's called asynchronous because the rotation speed of this cage here is, well, in the case of a motor, it's a little bit slower than the rotation speed of the magnetic field here, and if you have a generator, it's a little bit faster. And actually, this difference in rotation speed transforms directly also in the efficiency. When both have the same rotation speed, then of course no electricity is generated, but the efficiency would also be highest. So this is a trade-off between these two things. But it's clear why it's called asynchronous. Well, and if there's an asynchronous machine, then there also should be a synchronous machine. And this was invented by Friedrich Haselwander, an engineer. And there, the point is, that it's like a stepper motor, right? So this rotor follows exactly the field here outside. So there is actually a sad story about the invention of the synchronous machine. You can have a look at it in the Deutsche Museum in Munich, but at the time when it was invented, it was a competitor to established other techniques, and so the big companies did everything in order to suppress this invention with all kinds of tricks. Dirty tricks, actually. But, well, at least he got the honor, not the money for his patent, but perhaps in the long run the honor is more worth, I'm not sure. Okay, so this is a synchronous machine. And now, concerning, let's write up a few things first. So the iPad here. So we look first at windmills that work with an asynchronous generator. So the first point would be concepts with an asynchronous generator. Yeah, and we just call it ASG. Yeah? So, and the simplest one would be, of course, to directly connect the generator to the grid. Yeah, so direct grid integration. Yeah, so it's just yeah, connect the wires. Well, but it's not so easy actually. But let me just grab a graph that would show that. Yeah, so something like this. Yeah. So we would have here, of course, the rotor, then a gearbox. A gearbox, why? Well, in order to, this turns only rather slowly, yeah, a few times per minute or so. And then, of course, induction, you know, Faraday's law, there's the temporal derivative. So it is worthwhile to transform the rotation speed. And here, this is a planetary gear, so it should indicate here planetary gear. Well, I try to draw it this way. Yeah? And then it would produce alternating current, symbolized by these few lines here. But the problem with that is that the grid has a fixed frequency, and it is very important to keep this frequency, well, in step lock. You may have heard that a few weeks ago, I think, there was well, a close to disaster because one line in Europe suddenly switched off, right? And then the frequency, the grid frequency dropped from, well, from 50 hertz to 49 something. Yeah, and this can lead to the entire to the collapse of the grid and to a huge blackout. So if one wants to connect a power source to the grid, one has to make sure that you have the right frequency. And therefore, the original Danish concept, and it was Joule, so the pioneer, one of the pioneers of wind energy, after the war, certainly the most, one of the most important pioneers. Yeah, so he designed this three-blade design of windmills, and he also designed this grid integration at that time. So what they actually had to do was to use two asynchronous machines, and they had to, so once the rotor plate was fast enough, or the wind was fast enough such that the rotor plate started, they actually had to drive it to the right rotation speed, and only then they would be able to switch it to generator mode, and if the wind would be strong enough, they would actually switch to the stronger machine. Yeah, so this is the direct, so direct grid connection, direct grid connection. And this is called the Danish concept. And goes back to Joule and the Gates wind turbine. Maybe I have time to make a few historical remarks about this Geze wind turbine towards the end of this lecture. So what are the advantages? Well, the most important advantage is that it's a simple design. Yeah, so you don't need any sophisticated electronics, which was not available at the time Joule built this windmill shortly after the Second World War. Yeah, so it's simple and does not need sophisticated electronics. But it has huge disadvantages. One disadvantage is, of course, that you can't switch the rotor speed. Yeah, so it has a fixed rotor speed because the rotor speed is more or less directly. Yeah, so just disregarding this little bit of phase slip between, because it's an asynchronous machine, right? So the rotation speed is fixed. And this is, of course, a problem for efficiency because we learned that a windmill is actually designed for a certain tip speed ratio. And if the wind speed would change, then you would change the rotation speed, and this is not possible here. And the other problem that is actually connected to this problem is that this windmill would be quite sensitive to wind gusts, which in effect will limit this design to smaller wind turbines. So less than, say, 100 kilowatts or something like that. So the disadvantages: fixed rotation speed, because it needs to be locked to the grid, and sensitive to gusts. So what you should keep in mind is that the electric concept of such a windmill has actually consequences also on the mechanics. So if the electricity generation, so if the electrical part is not flexible and does not smoothly respond to different wind speeds and thus to different mechanical loads, then this has a back effect on the stress on the entire machine. So this is a really serious problem. It is also a serious problem because the electricity, the quality of the electricity that you generate is not very high. So reactive power, so Blindleistung is one of the problems. So, and this would be, as I said, this would be one of these Squirrel Cage machines. Well, the next thing that you could do is something more sophisticated, much more sophisticated actually. And let me show this here. So the next concept here depends already heavily on modern electronics. So what you would do would be just to, transform the alternating current that comes out of the asynchronous generator into direct current, and then you would transform it back to alternating current, right? And then it doesn't matter which frequency here which frequency the asynchronous generator would deliver, because you can always convert it to the right, to the grid frequency. Right? And this is, of course, only possible since sophisticated electronics is available. And one of the pioneers, this might surprise you, one of the pioneers in this field is actually a locomotive. Yeah, so this is the 120 series locomotive, which was researched in the 1970s and introduced in the 1980s. I remember this very well, when this unfamiliar kind of locomotive suddenly appeared. Well, actually, railway companies, they have the same problem. At that time, it was still Deutsche Bundesbahn, a public, well, it's still public, but it was hoheitlich, so it was, employees were Beamte at that time. So what's the problem here? The problem is that the electricity in the wires is, of course, one phase. And it is known that three-phase motors are much more efficient than one-phase motors. Right? So this is one of the problems. And what was done in this locomotive, so there's sophisticated electronics similar to the windmills in some sense. So you just transform it to every kind of current you like. Yeah? So you take the alternating current, I think it's just 16 hertz for the railways, and it's probably rectified. Yeah? So you produce direct current, and then you produce three-phase current out of that. Yeah? And then one can build such efficient locomotives. It held world records in speed, yeah? And it was designed as a universal locomotive, being able to run heavy trains and just passenger trains as well. So this can be done. Yeah. So let's write that up. Yeah. So a squirrel, squirrel cage asynchronous generator with DC conversion. Yeah. And then, of course, the rotation speed is adjustable. Yeah, so some huge advantage. The rotation speed is adjustable. Also, the reactive power is adjustable. Die Blindleistung is adjustable. Yeah, and of course, the grid companies like this very much. Right? So they actually had to pay penalties for the above design because of the low quality of the electricity it delivers. Rotation speed is adjustable, actually not very adjustable, but 0.8 to 1.2, 20% back and forth of the nominal rotation speed. Yeah, and then there are even more sophisticated designs, namely where a design where you actually put a resistor into the squirrel cage, and then it's actually possible to adjust the rotation speed even more. And of course, a resistor always produces losses, and so there are more advanced designs, particularly put forward by the company Vestas, which is the biggest wind mill producer in the world, Danish company, meanwhile also associated with Mitsubishi Heavy Industries. So, and what is done is actually something like this here. Yeah, so the power that you generate, so you use the electricity that's generated in the squirrel cage, you use some of that, right? And this is then called variable slip control, and can either be done by adjusting the resistance in the squirrel cage. Then, of course, you need to use a more complex scheme than just the squirrel cage. The squirrel cage is very simple, not connected to the outside, but if you want to adjust a resistor there, introduce a resistor there, then you have to connect the squirrel cage to wires outside, to circuitry outside. So this is here variable slip control. Yeah, so you know the slip between the rotor and the grid, basically. Variable slip control via adjustable resistors. Yeah, when I say adjustable resistors, then I mean, of course, semiconductor devices, some thyristors or transistors. In the squirrel cage, or which is the modern version, feed some of the electricity produced in the squirrel cage also to the grid. Yeah? And this is called a doubly feeding asynchronous machine. So feed some of the electricity generated in the squirrel cage also to the grid. Yeah, and this is then called OptiSlip. And I think it's a patent, probably long expired, a patent by, so OptiSlip for gusts, for gust control, and I think it's a patent by Vestas. So, and it's called doubly feeding asynchronous generator. Yeah, and it's clear where this name comes from. Now let's go to the synchronous machines. Yeah, so second, concepts with a synchronous generator. Concepts with a synchronous generator. SG. Well, and you can in principle start in the same way, just couple it directly. And well, this is very problematic, yeah, because the synchronous machine is really fixed to the wind speed, and so the feedback of this. So this is a very rigid situation, and this is bad for the grid, and this is also bad for the windmill. But nevertheless, we can of course show this sketch of that. Right? No, this is not what I meant. Actually, I don't have it here, unfortunately. Well, doesn't matter. Yeah, it's not an important thing anyway. Yeah. And the next thing would be, the disadvantages is a very rigid connection to the grid. Yeah? And this has disadvantages for the grid and for the stress on the machine I don't think that there are any advantages compared to the asynchronous concept. Yeah? So I'm not sure whether anybody has used that. I don't think so. And the next thing, similar to what we discussed for the asynchronous machine, would be just to use this synchronous machine, let it run at which speed it wants, more or less, yeah? And then convert this alternating current on whatever frequency to direct current, and then convert it back to the grid frequency. Yeah? And we actually distinguish, well, two combinations which gives then 4 scenarios. What you could do is, and actually this is already indicated here, what you could do is to just, well, leave out the gearbox and use a synchronous generator which has enough poles such that you can efficiently generate electricity, but because you don't care about the frequency, more or less, yeah, this rotor can run it at its optimum rotation speed. Yeah, so actually here 2 things are done. Yeah, so the grid is left out because what you need to do then is to increase the number of poles. Yeah, you get a huge a machine, of course. Yeah? So if you use, instead of say 12 poles, if you suddenly use 80 something, then you can imagine that this generator gets much larger. But of course, if you don't need a gearbox, then this makes the design much simpler. So this is one thing that you can do, and the other thing is that you can use 2 different kinds of synchronous generators. The usual way is that the magnetic field is actually generated by external excitation. So in German, this would we would say fremderregt. Or you can use permanent magnets, and then this would would be a permanent magnet drive. So several options here. What we have here is a synchronous generator with DC-DC conversion. Yeah, and then there are several options. What's called direct drive, which means no gearbox. And the other thing is direct drive or using a gearbox. This is one option. And then separately excited, so fremderregt. Or permanent magnets, permanently excited, yeah? Permanent magnets. And guess what? The most modern design is to use permanent magnets and not to use a gearbox. Yeah? So the most modern design, probably not everybody agrees, but if you are particularly concerned about maintenance, for example, for an offshore windmill, then you certainly want to avoid a gearbox. Yeah? And on the other hand, this means that if you build a really huge machine, say with more than 10 megawatts, then of course the size of the generator becomes really large. And if permanent magnets are used, you can build it much smaller. So the most modern design is permanent magnet direct drive. And all huge windmills, so the 10 megawatt class, they all rely on that technology. Permanent magnet direct drive. Yeah. Well, advantages are clear, right? No gearbox, maintenance, no gearbox. This has maintenance advantages. It's also not so loud. Yeah? And the other thing was permanent magnets. Yeah, I should have written no gearbox. Yeah, but the downside is on this a large generator because many poles are necessary, are required. It makes also the generator more expensive. Yeah? Large generator, large and more expensive. What you save on the gearbox, you might, well, probably the costs of the generator, this more than outweighs the savings on the gearbox. So, and then the permanent magnets. The advantage is smaller design smaller design and actually a little bit higher efficiency. Because if you have an electrically driven magnet, then of course you always have to take into account ohmic losses. So higher efficiency. So permanent magnet motors, they are actually the most efficient motors known. And this also applies for small pumps or something like that. So if you want to have, or for cars, so they use the same design principles. So smaller design, higher efficiency. What's the disadvantage? Well, in order to have a strong magnet, you need rare earth elements. So expensive and sometimes unreliable sources on the market. So expensive and difficult market. That's not very nicely written here. So expensive, rare earth elements are necessary, and their market is also problematic. Good. So this concept here, which increasingly dominates the market, so this concept here, this was introduced by the company Enercon. So here we have the machine on which this was first demonstrated. This is the E40 Enercon, and this is a pioneering machine. And the man who designed this concept is Alois Woppen. He's an electrical engineer, so he was he is an expert in this kind of technology, and his company starting as a very small company, just a few engineers started this company Enercon, which eventually became the largest German wind plant company, and this also made him rich. So he's a billionaire, but actually, so he did it himself. So he didn't just inherited his fortune, but he did it himself. Okay. So and this was also this typical design. So you see this large rotor, right? So they had to they put it into this enclosure. Later, a few years later, they would have another design, which they actually asked a famous architect, namely Norman Foster, who also designed the cupola on the Reichstag building. And then Enercon for a long time, until very recently, had this egg-shaped design. So that you also see here on this title page. Okay, so one other remarkable thing that Enercon did is that they changed the blade design here a little bit, right? So it's also characteristic for these Enercon windmills. So between this E66 and E70, so they added a little bit of blade chord lengths, and because they discovered that this will bring a few % of more efficiency. Okay, well, so much for the concepts of electricity generation. I think it's time for a brief break, 5 minutes or so. See you in a few minutes. . 。  . 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 。 。 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 . 。 .
。
Yeah, let's continue. The next thing I wanted to discuss is something that you often find in literature on windmills, or, well, if you look at the material, the marketing material that or wind energy companies would distribute, they have to state for which conditions their windmills are built, right? And this is called wind classes. So, and this will be the next chapter for today, namely 8.2 wind classes. And in this connection, I also want to discuss capacity factors and things like that. So, 8.2 wind classes and capacity factor. Now, there's no direct connection between both, but anyway. So, and capacity factor. We distinguish more or less 3 wind classes, and the class 1 are the strongest winds, and class 3 are, well, still sizable winds, and actually some people also talk about class 4, which then would be even weaker winds. And each of these classes is actually subdivided into the amount of turbulence that you have there. Right? So weak turbulence, medium turbulence, and strong turbulence. And this is, and both are important because this leads, so turbulence as well as high wind speed, they determine, of course, the stress on the machine and thus its lifetime. So the machine needs to be certified for a certain wind class. So let's make a table here. So we have the wind class, wind and turbulence class. And of course, they correspond to an average wind speed, and it's measured at the height of the hub, at the height of the rotor axis. So average wind speed at the axis. And yeah, so what we have is here class A, 1A, and this is high wind. And high turbulence, so 18%, I'm not exactly sure how they measure that. What it means is an average wind speed of 10 meters per second. Yeah? And then 1B would be high wind speed and a lower turbulence. 16%. And of course, average wind speed would be the same. Then the next thing would be 2A and B. So this would be medium wind speed and is defined as 8.5 meters per second. And again, turbulence here would be 18%. And here 16%. And finally, we have low wind speed. And there also the same thing, A and B, 18% and 16%. And here the wind speed is 7.5 meters per second. And some people also use class 4, and this would be 6 meters per second average wind speed. So this is probably, so the last one is probably economically not so interesting. Okay, well, of course, such a windmill needs to be designed for extreme wind conditions, so its survival needs to be specified for much higher wind speed. And the figure that's used is the 50-year gust, the extreme 50-year gust. And what one assumes is a factor of 5 to 7 times higher. Yeah? So the windmills should survive extreme 50-year gusts. And by definition, so they are 7 times the average wind speed. And of course, a windmill in a typhoon area or a hurricane area probably needs to be designed for even higher wind speeds. Yeah, and there it's not just a gust. Yeah, so such a hurricane can have sustained wind speeds, probably in excess. So if this is 70 meters per second, yeah, this is a high wind speed. Okay, let's come to the capacity factor. In German, this corresponds approximately to Volllaststunden. Yeah, so if you have a 10 megawatt windmill and it would run at its capacity at 10 megawatts throughout the year, then it would have 8,760 times 10 megawatt hours produced. Yeah? Of course, so this would 87,000 megawatt hours or 87 gigawatt hours of electricity would be the full capacity of that machine. And of course, we know that if the wind doesn't blow, it can't generate electricity. So the real number, the actual number of generated gigawatt hours will be lower than the entire capacity. And the ratio is the capacity factor. So let's define that. Capacity factor. So the definition is the ratio of the rated power times 8,760 hours and in the numerator we have the actually generated power or generated electricity, not power, electricity. So electric energy. Yeah. Just a number on that. It's actually quite simple to look up the average capacity factor of, say, German windmills. And until 2012, this was a rather disappointing number. Namely, it was lower than 17%. It was lower than 17.5%. Yeah, so just below 17.5%. Yeah, And this gives you an idea that such a windmill is kind of expensive because it operates with full power only less than 20% of the time. So as a number here, until 2012, all German windmills together had a capacity factor of less than 17.5%. Scottish windmills, of course, they have more wind than we have. They were at 24% or something like that. Okay, now let's look at some more on some modern windmills. So one example would be an Enercon machine, a modern Enercon machine, namely the E147 EP5. So the nomenclature of almost all companies is pretty similar. E stands, of course, for Enercon, but 147 stands for the diameter of the rotor in meters. So a rather big windmill here, and EP5 stands for that it's in the 5 megawatt class. And this windmill is for the wind class 2A. So not very close to the coast. So kind of medium wind speed. And now I looked it up on Wikipedia. So what they say is at 7.5 meters per second average wind speed, this machine is expected to produce, now what was it, 17.2 gigawatt hours. And this is for, so there are different models with different sizes of generators. And this is for the 4.3 megawatt generator. And now we can calculate. Now we can do the calculation. So we would take the capacity, the full capacity. That would be 4.3 megawatts times 8,760 hours. This gives approximately 37 gigawatt hours. And then the capacity factor. So instead of these 37 gigawatt hours, we just produce 17. And this means that the capacity factor is 17.2 divided by 37. And this is 0.46. So that's not so bad. So that's much better than any solar panel, of course. Okay, well, let's look at another Enercon machine. And I have a slide for this machine. So this is this used to be a world record machine. So this is the Enercon E126. It's no longer produced. I think it was not a very successful model. and probably we understand why this is so. It's a huge machine. Yeah? So at the time it was invented, or it was built. It was the largest windmill in the world. Yeah, so diameter, of course, 126 meters here. The weight of the machine house, 360 tons. Yeah, so the blade of each, yeah, so each of the rotor blades had a weight of 64 tons. This is like 3 battle tanks, heavy tanks, 3 Kampfpanzer. So on each of these things, unbelievable. Yeah, and the power was, first it was rated for 6 megawatts, and then they had versions with 7.6 megawatts. And if you drive on the A9 close to, before Leipzig, there's the wind park Stößen, and there you can see 3 of these machines. So they kind of look, so if you look at them, they kind of look gedrungen. So they are not so elegant than other machines. Okay, so let's calculate the capacity factor of this machine. So another example, that would be the Enercon E126, which has a power of 6.7 megawatts, right? And then the capacity factor. So what they expect, so expected annual electricity production, 17 to 20 gigawatt hours. And then the capacity factor is less than 30%. And this already indicates why they probably discontinued, apart from, these enormous, the enormous weight of the blades. I think one would build these blades with, approximately half the weight today. But nevertheless, let me show you one graph that's interesting in this respect. Namely, I looked at a few Enercon windmills because I found them nicely collected on Wikipedia. And what I did was that I calculated for each of them the ratio of the power, of the rated power. So in this case, it would be the 6.7 megawatts. Right? And divided this through the square of the diameter or the radius. Yeah? So then you get an idea on the strategy on how to design a windmill. In order to increase the capacity factor, what you have to do is, of course, to collect also efficiently wind with low wind speed, right? So you would choose a smaller generator and use a larger swept area, a larger catch area for the wind. This is actually what you see here, right? And this dot here, actually, so this dot here, This is actually the Enercon E126. Yeah? And what happens over the years is that people made that ratio smaller and smaller because, well, what one does is the following, another graph for that. Yeah, you remember that graph that I showed actually last time for a particular real machine. So these were data by the producer. So just let me go back a few slides here. Yeah, so you remember probably this one here. And we see this typical curve here, right? That, of course, as the wind gets stronger, we have this cubic rise here. But then, of course, as we approach the capacity of the windmill, this curve has to go into saturation in order not to exceed the capacity. So what you would do in order to get this saturation behavior would be that you pitch the blades such that they are no longer at the optimum angle. Yeah? If you don't do that, then you destroy your generator, but probably before you destroy the generator, the windmill would be thrown over because the thrust on the windmill, as explained a few lectures ago, will get too high. And actually this happened sometimes. Right? So if the windmills are not properly maintained and if this pitch control doesn't work properly, then then there's a problem. Okay, now what people do is of course that they move this curve here in this direction. Yeah, so just by installing a smaller generator on a larger diameter. And this increases the capacity factor, and of course this makes a lot of sense because what you want to have from an electricity generator is that it reliably generates electricity, which means that it has a high capacity factor. Yeah? So no power plant has a capacity factor of 1, but a capacity factor has a usual power plant perhaps of 80 or something like that. Yeah? And so 15% is actually, in German I would say, a Zumutung to society, because this means that you put a lot of external costs on other market participants. This was kind of okay as long as wind power didn't play a major role in the grid, but of course this has changed, and therefore also the policies had to change. Well, what's the situation today? So for even more more modern windmills. So I show two or three other examples. Yeah. So this is a windmill by General Electric. You know, the usual business of the famous companies in power plant and generator building, namely General Electric and Siemens, that they all have problems with their traditional market. Well, to a good part because of alternative energies. But these companies, they are clever enough and also entered the market of windmills. So here you see a windmill for offshore wind power generation. And to date, I think it's the strongest, so 14 megawatts. With a diameter of 220 meters, right, so there are different versions here. Well, the total height, 260 meters. And what's remarkable is the capacity factor. So I have capacity factors of more than 60%. So these, I was really impressed when I saw that. So offshore windmills, huge devices. So do they say something about the weight of their gondola? No, it's not. So offshore wind class 1C. Remember, 1A was high wind speed with a lot of turbulence. Now here offshore, so there's not much turbulence over water, but of course high wind speed. So this fits to what we have discussed. So here just another nice picture. So these are the ships that are used in order to erect these windmills offshore. Here another windmill with a dramatic photo. Probably it's photoshopped. So the propaganda division of Siemens Gamesa company, headquartered in Spain. And this will be the strongest windmill once it is in serious production. So far I think there are only prototypes of this machine. So in 2 or 3 years they will hit the market. So the British, they built several wind parks in the North Sea, and some part of that wind park will be equipped with the General Electric windmill, and another part with this one here. Right? Weight of the machine house 500 tons. I didn't find any information on the weight of the rotor blades. Would be interesting. But I guess it's actually not the 65 tons, also the length is, perhaps it's 65 tons or so. But it's not 100 tons or something like the Enercon E126. Of course, there is some time, some development time has passed, but nevertheless, so you see the progress. And finally here, Mitsubishi Heavy Industries, Vestas windmill. So Vestas, this big Danish company, they run their offshore activities together with Mitsubishi Heavy Industries. And this here is a 10 megawatts machine, rotor diameter of 164 meters. And you see the blades, they are much less heavy than a much shorter blade by the Enercon wind machine. And here, well, it doesn't have that much power as compared to the General Electric and the Siemens Gamesa. But anyway, so it was a big machine. So once again here, the Enercon. Now, finally, let me come to one topic of wind power, namely the question of acceptance, of societal acceptance of wind energy. And I would like to briefly discuss 2 points here. Perhaps we start with kind of, where do I have this slide here? So let's start with this slide here. All right, so what you see is, didn't finish quite. Yeah, so what you see is quite, well, you might say an ugly picture. Even I would say so. Yeah. So I often say that I like the aesthetics of a windmill, but windmills in this arrangement here, right? Different types of windmills. So this is probably an Enercon 126, I guess. Yeah. So from its appearance here, maybe this also. So different windmills and arranged in an apparently arbitrary way. This doesn't look very nice, I would say, right? And of course, other people also think so. And this is certainly one problem for the acceptance of wind energy. Well, and I have to say that that it's of course, the wind industry is interested in selling windmills, but then they also should care about how their machines look in the landscape, right? Of course, those people who criticize that are typically the people who don't criticize this side here, right? So mining, so they dig hundreds of meters deep holes, remove entire villages just in order to produce more CO2. Right? The same people who criticize this here tend to not criticize this here, but of course this is no excuse for this situation. There are actually people who thought about that problem, and I bought a book recently. I saw a book, so this one here, Wind Energy and Landscape Aesthetics, and yeah, at the end of this book you would find a number of rules that one could consider in designing a wind park, such that that it doesn't look like here. Okay, another point that I would like to discuss here is that they should not only look kind of beautiful, right, but actually the neighborhoods who have to look at these windmills, and some people always won't like them, then at least they should be compensated in some way. Right? So the cities or the villages with a wind park, they should profit also financially. It's not a good idea that some people have the profit and the others have the difficult parts or the disadvantages of these industries. So what you see here is the business tax, and initially the case, so a few years ago, initially the business tax was collected by that community, by that city, where the company had their headquarters. Right? And then a company sitting in, say, Munich and owning wind parks in Thuringia, and this would mean that the communities here in Thuringia would see nothing of the tax. Right? This has changed, and now actually at least 70% of the tax goes to the respective community. But I think this is still not enough. They need to do more, because it takes many years after building the windmills until actually tax will be paid, because the investment is first compensated with the tax. Yeah? So initially they have no revenue, so no Gewinn, yeah? these businesses, and therefore they don't pay tax in the first few years. And only after 7 years it starts slowly, and then eventually the windmill, the windmill has is out of the books, and then it goes down again. You see, this is not a good situation. So, and people have to think about that. Yeah, I guess this is pretty much all I wanted to say. I could say a few more things about the history of wind energy, but I think I made already a few remarks. So remember my remarks concerning the Grovian, so the große Windanlage, one failed project. Well, actually, I would like to show at least one funny thing in this respect. So where is my mouse? Here is the mouse. So you see, here we have again the Grovian. And you see also the Secretary for Research at that time, and later Finanzminister Hans Matthöfer in the cabinet of Helmut Schmidt. So Helmut Schmidt, the former chancellor, he believed in nuclear power till his death a few years ago. But anyway, so here is this große Windanlage, and I made a few remarks concerning the net that was erected between these two towers. So if you read the literature, then it says that they measured wind speed with that. But then you ask yourself, why do they need two of these towers? Well, because they wanted to protect the birds from that. But this is not the point that I wanted to make. Pretty much at the same time in Denmark, the Twintkraft windmill was built, and it still runs today, right? So, and here's a press release of this, it was actually a community project. Yeah? So on March 29th, 1975, we cut the first sod in Twint to create the world's biggest windmill. The same year, the Swedish nuclear plant Barsebäck went into operation. Yeah? On May 29, 2005, 30 years later, so this anniversary, a few days later, the Swedish nuclear plant stopped operating. Twintkraft keeps on running as it has done for the past 28 years. Read more and so on. Yeah? And now the funniest thing is that this was actually a community project. So these were, you would say, hippies who were dissatisfied with nuclear power and wanted to demonstrate an alternative, right? And so the Danish hippies they disproved German engineering. So this is really, really a funny thing. Okay, I think this could be the final remark here. Thank you for participating in this course. I hope you have luck with the final. I also hope in particular, I think this is more important, that you enjoyed this lecture, that you learned something. If you're interested, at 6 o'clock, so in 15 minutes about, I would offer another Zoom meeting where we can discuss whatever you are interested in. Thank you.